Good morning, good afternoon, good evening. Welcome you to the October RWG meeting. Got a good topic today, talking on resilience and loss-driven system engineering. Our presenter is John Brits. John's a system engineer who recently retired from the MITRE Corporation in Colorado Springs. He has degrees in physics engineering, nuclear engineering, and systems engineering. He's worked in the nuclear power industry where he specialized in radiation safety, and in IT industry where he focused on artificial intelligence applied to complex engineering decision making. And in the system engineering consulting arena where he supported aerospace and Department of Defense activities focusing on system resilience. John is the past chair of an INCOSE Resilient System Engineering Working Group and currently continues as a co-chair. John's an expert contributor in the ISO working group developing standards on resilience and is PM for the INCOSE Loss-Driven System Engineering Project. John's a registered professional engineer, a project management professional, and a certified system engineering professional. We look forward to your presentation, so I'll hand it over to you, John.
Thank you for this opportunity to share some of what we've been doing in the resilience and the loss-driven systems engineering area. I will be talking about, first of all, what the current thinking is in the INCOSE resilience community with a focus on requirements. I think people here might be interested in some of the work we've done on resilience requirements. I think you're going to find this interesting. Resilience requirements are an interesting challenge, and we'll get into how we can address that. By the way, if you're interested in resilience, I certainly encourage you to join that working group. And then I'll talk about the loss-driven systems engineering project, which was approved by INCOSE last March. We now have an official project to develop some products on this topic of loss-driven systems engineering and influence the way that the various loss-driven specialty areas work with one another in the future. So anyhow, let me jump right in. Okay, just to get everyone on the same page, let me start out by reminding everyone what we're talking about when we're talking about systems. A system is an aggregation of system elements that come together in a particular configuration, and when you do that, magic happens. You get a capability out of the system that is something that in general the stakeholders want to see. And we also all know that the system depends on the environmental conditions within which it operates. And most often, a lot of the design of the system is targeted at achieving the required capability during nominal conditions. But sometimes the system is having a bad day. Sometimes the environmental conditions are going to potentially degrade the capability generated by the system. And that's what resilience is all about. Resilience is about how well the system delivers required capability in the face of adversity. Let me define that term. Adversity, for the purposes of resilience, is anything, literally anything that can degrade the desired capability of the system directly or indirectly. I'll be using the term adversity quite a bit. Now, how do we define resilience? There are many different definitions out there in the community. A number of them are good definitions. There are a lot of bad definitions, by the way, and well, yeah, I won't mention where they are. But within INCOSE, I think we've got a pretty good handle on the concept. And the definition that the INCOSE Resilience System Working Group has decided to work from, a good working definition, we think it's a good definition because it supports the concept of systems engineering very effectively. The definition is, quote, resilience is the ability to deliver required capability when facing adversity. It's not that complicated, but it does imply a few things that we're interested in. We're interested in what that required capability is, and what that required capability is when we're in the middle of an adverse situation. Now, there are a couple other aspects of the meaning and scope of resilience that people have different opinions on. The scope of resilience that we in the working group have adopted is that it includes the ability to avoid adversity, withstand adversity, and recover from adversity. And we're well aware that some people will argue, well, no, resilience is really only recovering from adversity. But other people will say, no, it's both withstanding adversity and recovering from adversity. We in the working group strongly believe that we should have a full aperture understanding of the scope of adversity that includes avoiding withstanding and recovering. Some people refer to the avoiding idea as proactive resilience. We could spend easily an hour discussing this. I think I could convince you pretty effectively that this is the best position the engineering community should take, because quite honestly, when it comes to achieving resilience, we want to do anything that works, and that does include the avoiding potential. One other thing worth mentioning is, and this is a foot stomp, the objective of resilience is the required capability, not the system stasis or integrity. There was early on, when the term of resilience was being used within the engineering community, some people were arguing that it was all about the equilibrium or the stasis or the integrity of the system. But as time went on, people realized that no, sometimes you achieve resilience by adapting to the adversity, by actually changing the architecture or configuration of the system to deliver the required capability. And as a matter of fact, sometimes you will sacrifice part of the system itself in order to achieve adversity. So here again, we believe we should expand the overall scope of adversity to include both system stasis and also anything that can help achieve the desired objective of delivering required capability. Final thing to mention about the meaning of resilience, we do believe it's a concept that applies very, very well and should be applied to all engineering system types: cyber, physical, organizational, and conceptual. And while I'm on the topic of what it applies to, one other dimension that should be considered, I'm going to add it to this slide, is resilience is a consideration at all levels of aggregation. It can and should be applied at the system level. It can and should be applied at the system of systems level. And it can and frequently should be applied even at the system element level, the part level. A part can be resilient. And so it's a concept that can be applied at all levels of aggregation. For those of you who, like me, think more graphically than in terms of the written word, here's what resilience looks like. We know, once again, the system delivers a particular desired capability. The acceptability of that capability is judged against what the required capability is. And if an adversity comes along and stresses the system, it may degrade the system's ability to deliver the required capability. And this is what resilience is all about. How well can the system deliver required capability when faced or stressed by an adversity? And by the way, I snuck a new word in there, and that's stress. For those of you who are mechanical engineers, you know all about what stress and strain are. In the resilience area, it's a useful term because an adversity can be either direct or indirect. And it's useful to have a term that applies to the adversity that directly affects the system. One interesting thing about resilience, which may be of interest to those who are trying to develop resilience requirements, is the fact that many of the parameters relating to resilience are really dynamic. Resilience is usually discussed in the form of a resilience scenario. You could consider it a mini ConOps about the way the system delivers resilience capability. Let me just show you a graph where I'm going to plot time on the horizontal axis and capability on the vertical axis. We talked about required capability earlier. Oh, by the way, I should mention that one of the things the engineer has to do with any scenario is identify what the useful scenario period of interest is. On this particular plot, I'm now showing the required capability. This is purely notional and it's hyper simplified. But the important point here is I'm showing that the required capability over the time period of the scenario may change. The required capability can change. For those of you who are at all involved in the military, you know that, for example, if you've got an air campaign in a particular area, early on in the air campaign, you need a lot of communication capability. The required capability for comms is very, very high. But after the second or third day, when you've achieved air superiority, the comms bandwidth required goes way down. And so To understand the overall resilience scenario, it's very important to allow for the possibility that the required capability may change as a function of time. Now, the same is true for the stress that is applied. Now, I'm plotting stress on the vertical axis, and I'm showing stress over on the right side of the plot. The stress in this notional example starts out at 0. It goes up to a peak, it tapers off, and then it goes back down to 0. It could be almost any shape. There could be multiple stresses. They could occur at multiple times throughout the scenario period of interest. But the important thing is stress is a variable as a function of time. And it can be a very complex variable as a function of time, and that needs to be considered. Now, finally, the notional plot of the delivered capability. The capability starts out at a nominal level and goes horizontally. And then the stress on the system starts to take hold and the delivered capability is degraded. It goes down to a minimum. That minimum shown here is actually below the required capability. That is not a good situation. But then the stress ends, the recovery capability of the system or the system of systems within which the system exists takes over, and the capability delivered by the system rises again above the required capability level. And I'm showing a rather rapid rise for a time period and then a long-term slower rise. But it could be anything. The final capability may end up being higher than nominal, lower than nominal. It depends on what the objectives are of having that margin between the maximum required capability and the maximum delivered capability. There are times, one way you can achieve resilience is by providing margin between the required and the delivered capability during nominal conditions. We refer to that period when the delivered capability is below the required capability as the period of degraded capability. With that as background, I'm going to talk a little bit about resilience requirements. They're complicated by the fact that the parameters in the requirement can change as a function of time, but they're also complicated by the fact that a resilience requirement is really a requirement about a requirement, and I'll explain that through an example. One example of a resilience requirement could be based on the delivery of electrical power to a household. That requirement for delivering electrical power to a household during nominal conditions would probably include a statement about the required voltage, the required amperage capability, the accuracy of the frequency, the quality, the amount of noise in the delivered power. And that would be the fundamental requirement that the stakeholder is interested in. I want so much voltage and so much amperage and at a good frequency. But during a resilience scenario relating to that particular capability, let's say you have a storm that knocks the power out and you have a blackout. You now have a new metric that you're interested in. The metric might be the length of the blackout itself. And so you have the fundamental capability of interest and then a second requirement about how well that capability is delivered during an adverse situation. And in the case of the power being delivered to the household, the length of the blackout would be a good metric. And as a matter of fact, if you wanted to decide, well, what's the target for that blackout time? What's the maximum blackout time that you would be willing to accept and still consider the system somewhat resilient? You might say, well, I think we need it to be 4 hours. And why 4 hours? Well, because after 4 hours, the frozen food in the refrigerators in the homes may start to melt and become unsafe. And so we really want to make sure that the system is sufficiently resilient to make sure that under any condition, we move out of a blackout situation within 4 hours. Just to throw it out there, another metric that might be of interest would be the voltage itself. How much of a brownout can we withstand? How low can we allow the voltage to go? And the answer to that might be, well, just notionally 90 volts. And the reason behind that might be because when the voltage drops below 90 volts, induction motors tend to overheat and we can end up destroying induction motors. And so we may have a resilience requirement that the voltage not decrease below a certain level in the face of adversity. But once again, coming back to why this is such a complicated requirement pattern, it's because we're actually talking about a requirement about a requirement. And with that, let me walk through this particular requirement pattern. By the way, while I was still working for MITRE, I and my two co-authors, Mike McEvely and Michael Pennock, developed these requirement patterns at the request of OUSD, the Office of the Undersecretary of Defense, because they were having trouble writing resilience requirements, and they asked MITRE to help them identify what's the needed content and structure for resilience requirements. And this is the structure we came up with. And the way this is read, the purple bracketed parts are where you fill in the blank. And so what we're saying here is the system, which may be in a certain mode, which could change as a function of time, and in a certain state, which could change as a function of time, encountering an adversity, which may change as a function of time, which imposes a stress, which can change on a function as a function of time, thus affecting delivery of a capability of interest. That's a fundamental capability. And that capability of interest has both a capability metric and a required capability target, which may vary as a function of time. During the scenario time frame and under the scenario constraints, shall achieve the resilience target for a particular resilience metric. So anyhow, that is the natural language pattern that we identified for resilience. Are there any questions about that? Does that make sense? And does it make sense that that is one of the complications for capturing the requirements for resilience?
How anyone can define resilience metrics or where it is defined? Like, how do we verify that or how do we follow that? Is it requirements to be gathered before we start gathering any requirements, or will it be system driven?
That's a real good point, and I will come back to that in a few slides. But let me right now just say resilience requirements are highly situational. They depend on the particular capability of interest and the needs of the stakeholder. You know, like I just mentioned, you might have a blackout length of time metric, and that's determined by the fact that you're worried about the food going bad in refrigerators. But we will return to the question of what the resilience metrics can be in a couple slides. We also delivered that pattern, that is the content and the structure, in two other forms. This is the one you could put it in front of a non-technical person, sort of, but at least it's readable in English. And they could say, yeah, that's what I want, or no, that's not what I want. And I'm going to skip ahead a slide. We also delivered it in the form of an entity relationship diagram. That is a data-centric representation of the exact same information for resilience metrics. We have a number of entities: the adversity, the time period, the system mode, the system state, the scenario, the stress, the capability, the system, the resilience target, the resilience metric. These all have attributes that can be captured and managed within a data structure. We also delivered it in a SysML extension form for that pattern. And as you can see, the resilience requirement, this is a stereotype class. It has the attributes of adversity, the system name, the stress of interest, the capability of interest, the time frame, the scenario constraint, the resilience target, and the resilience metric. And of course, each of these attributes has its own class that's not shown on this particular diagram. So our goal was to provide identical information in three different forms that met the needs of three different groups of people: the data managers, the SysML folks, as well as the people who can read English. And by the way, just to give you an example, when we were developing the pattern, we took two approaches. We did a deductive approach where we evaluated the actual meaning of resilience and its importance for the purpose of systems engineering, and we're able to deduce what parts of the content and structure of a resilience requirement would be. But we also identified 14 different exemplar requirements from the real world and analyzed them to see what they had in them. This is a requirement that shows up in 10 CFR 50.46. That's Title 10 Code of Federal Regulations 50.46. It is the acceptance criteria for emergency core cooling systems, ECCSs, for light water nuclear reactors. And let me just jump right down to paragraph A, where the requirement begins. Each light water reactor with zircaloy cladding must provide ECCS, emergency core coolant system, and that's a system of interest, designed so that the calculated cooling performance, that is the capability of interest following a postulated LOCA, that's a loss of coolant accident, that's the ultimate adversity, conforms to certain criteria in paragraph B. And then paragraph B actually identifies two criteria that must be met. First of all, the peak cladding temperature, and by the way, cladding, that's the fuel cladding within which the fuel pellets reside. That cladding is the first barrier to release of the radioactive materials that are formed during the fission process that the fuel pellets undergo. And so it's very important that you try to maintain the integrity of that cladding. And to do that, they want the peak cladding temperature not to exceed 2200 degrees. And now that is a resilience metric, that is a strain, and that is also the target. The target is 2200 degrees Fahrenheit. Secondly, the maximum cladding oxidation. Once again, this is the metric and the strain, shall nowhere exceed 0.17 times the total thickness before oxidation. Once again, here's the resilience target that you want to achieve. And now this particular requirement, I think it's interesting because not only does it show all the parameters, the metrics, the targets, and so on, it also, and I didn't include it here because it goes on for a couple pages, they provide the modeling assumptions that must be followed in order to verify that you have met this particular requirement. So the resilience target assessment method in this particular case is a part of the requirement. I think that's kind of interesting. That's something we need to consider more often than not. But anyhow, I just wanted to give you that example. This is one of, like I said, 14 exemplars we looked at, and we used them to develop this pattern for resilience requirements. Okay, let me go on to one other item. And this is one of the things that the Resilience System Working Group has been doing now for, boy, almost 10 years. We've been curating lists of objectives of resilience and design techniques, and I'll go into that in the next few slides, for resilience. In other words, providing a taxonomy of means of achieving resilience that can help the systems engineer or any engineer achieve resilience by understanding the different techniques that might be of use. And we have a three-layer taxonomy. The first layer is the fundamental objectives. These are things that should be considered very early on in the life cycle. These are the things that you should bring to the stakeholders and talk about them. How much of each of these do you want to achieve? And the three are avoid adversity, withstand adversity, and recover from adversity. If you're achieving any one of these three, you are achieving resilience. Now, the second layer of the taxonomy is what's called means objectives. And those of you who are used to decision theory, you understand there's an important reason to separate fundamental objectives from means objectives. I won't go into that right now. If anyone wants to talk about it during Q&A, we can come back to it. But the important thing here is these are objectives that tend to achieve resilience and should be considered as means of achieving the resilience that you're after. And the examples we have here include adaptation, anticipation, constrain, continue, degrade gracefully, disaggregate, evade, evolve, fortify, manage complexity, minimize adversity, minimize faults, monitor, preserve integrity, prevent, reduce vulnerability, repair, replace, tolerate, and understand. This is a toolkit of objectives that should be considered as means of achieving resilience. Each one of these could be requirements early on in the life cycle. And then finally, the third level is going even further into the design life cycle. These are architecture, design, and operational techniques for achieving resilience, and they are, no kidding, design, architecture, and operational techniques. It didn't make sense to give definitions for all of these, but information about these is available in the CBOC and in the Systems Engineering Handbook. And if you want any detailed information about any of these, feel free to contact the Resilience System Working Group. The point, I think, from your perspective is any one of these may require a requirement definition or a requirement specification. Let me jump now and spend just a minute or two talking about resilience metrics. Resilience metrics, I mentioned earlier, one was the blackout. The length of the blackout would be a metric of resilience. The brownout, the amount of brownout, the reduction of capability from a voltage perspective could be a metric of resilience. Resilience metrics are very situational. And frequently you'll want more than one of them to properly define what you really require of the system with regard to how it reacts to adversity. This is a list of them that we developed over time. You can see the reference at the very bottom. This again was done for the purpose of the Department of Defense and specifically for achieving resilience of space assets. I'm not going to go into the details of these. These were the ones that floated to the top after some very, very serious consideration by a lot of very, very intelligent people in the industry. The challenge is there's no way of predetermining what the required metrics will be. They depend on the system, what the capability delivered is, what the adversity is, and ultimately what the stakeholder really needs. However, and this is a true story. I was talking to a 4-star general about resilience metrics, and I said, sir, in this case, we probably need 4 or 5 metrics. And he looked me in the eye and he said, John, I want 1 metric. And I said, yes, sir. And the bottom line is, if you had to pick one best metric, and this is the bullet at the very bottom, the one best metric we would recommend, and that's me and the Resilience System Working Group, is that metric be the expected availability of the required capability. The reason that's a good universal metric is it is basically based upon what we mean by resilience. It does a very good job of capturing it, but if it makes sense to have other metrics such as the length of the blackout or the amount of the brownout, don't hesitate to do that if you can, because the more specific you can get, the better the chances are that you're going to be doing the right thing. Now, are there any questions so far on any of that? I'm going to switch over to talking about loss-driven systems engineering.
Hey, John, could you go back to the previous slide?
Sure.
So the last bullet, the expected availability of required capability when faced by adversity?
Yes. In the context of a resilience scenario, what's the expected availability of the required capability?
Okay, thank you.
And by the way, it's worth mentioning that Tim Ferriss, who's one of the members of the Resilience System Working Group, he actually has developed an approach to making this a lifelong definition of the resilience of a system. In other words, he doesn't just talk about a single resilience scenario. He talks about doing a resilience evaluation on the entire life cycle. And he's written papers and developed mathematical approaches to doing that. That can be a useful perspective. And if you're working with this, the expected availability of the required capability, we have a very specific mathematical representation of what this is mathematically. And so this isn't just words. We have a formal mathematical definition of what this means. And I think it's available in the CBOC. If it's not there, it's definitely available in the reference at the bottom of the slide, or contact me or the Resilience System Working Group if you're curious about what the formal mathematical definition is of this metric.
When I see the word availability and then like reliability, it's common for people to write requirements saying the system shall have an availability of something or other.
Yes.
Or reliability of something or other. But it seems like that requirement is meaningless if you don't address the adversity that could cause you to lose the capability.
Yeah, and I'm sorry. The way we think, that's just implicit. But I'm going to modify this slide to mention the adversity as part of that definition, part of that metric. All of these particular metrics are pointed at the thing you're measuring in the context of a resilience scenario, which absolutely is in the context of an adversity. So, yeah, but your point is well taken.
Hey, John, remember, one of the things we've learned in dealing with requirements over the years is anything that you think is implicit, well, it ain't. You have to be very explicit.
And I go back up to this pattern, the system encountering an adversity, but then you do get down to the resilience metric, which is a separate parameter. But I totally agree that to create a resilience requirement, you need to define the adversity of interest. You're both totally correct. Okay, and was there another question out there?
Yeah, John, I think you kind of touched on. I was thinking of, if you go back to your slide, I think it said required capability, which changes over time. So
Yes.
there's a time element there. And if you go back, I see how you have that time as a function of that. So that's just part of the more definition, I think, that gets teased out of that statement, correct?
Right, and that's what makes the creation of a resilience requirement kind of difficult and complex. You have this time factor that frequently does have to be addressed. You really may need so much of the capability during one phase of the scenario and a completely different amount during a different phase of the scenario, and that needs to be addressed. Part of the requirement.
So it could be multiple requirements.
Sure, that would be a strategy for dealing with it.
It may have been degraded because of the stress, and it
Yes.
degraded the performance, but then the system is able to recover. So, how does it go about recovering? And that also gets into understanding the behavior of your system architecture, the
Yes.
nature of the stresses, and being able to identify. I try to stay out of the shoes of the design team, but tell them everything they need to know how to design. And that's hard for us because we all want to design.
And let me add to what you said. The recovery may be organic within the system of interest itself, or it may be provided by the system of systems within which the system of interest resides. And both of those are legitimate, and both need to be considered as options.
And it may actually be the result of human interdiction.
Absolutely. And in those cases, the human and the training of the human should be part of the system. And by the way, you probably noticed before, I did talk when I was on the lower level of the taxonomy. We very intentionally talk about these are architecture, design, and operational techniques. Operation and training can be as important as the design and architecture in a number of these. So yeah, you have to take a very holistic view. And we have one more raised hand, Macaulay.
Thank you for the presentation. Appreciate it. Very nice, informative. Thank you for sharing this with us. I just have a quick question. So resilience is very nice, but do you also consider that designing scalability in your system, right? So that you be able to absorb the resilience, because you have to have provided necessary capability to accommodate that. Is that part of something that you think of when you are resilient?
Yes.
Because there has to be scalability as
Yes.
part of design so basically it will take what is necessary to deliver what you want to do. And that has to be part of your design as a whole. Is that something that you consider?
Yes, yeah, absolutely. And as a matter of fact, we'll talk about that a bit when we get into LDSE. But let me just point out that we consider change as a potential type of adversity. And that change might be a change to the environment. It may be the fact that the system changes over time. It may even be based upon the fact that the needs of the stakeholder change over time. And one way you deal with that is through adaptability. And so sometimes for the system to continue to deliver required capability as things change requires adaptability of the system itself. I think that's what you were getting at, right?
Well, I'm talking about, so basically, let's say that maybe my system at optimum performance will be, say, it will need 60% of whatever that it needs to get the job done.
Yes.
I know that is the maximum, but I want to design my system because I don't know that maybe I may have to get up to 70%. So I have to then design that excess capacity in my system to take this unintended, thing that may just happen, right? Because or else, if it is bounded of what I think the optimum load will be, how is it going to be able to deal with resiliency if it was to overshoot that limit?
Yeah, and so you would build a margin into it. And as a matter of fact,
Mm-hmm.
interestingly enough, margin is really a very, very useful way of achieving resilience. It addresses both known situations and frequently addresses unknown situations.
Exactly. Yeah.
And
The
so,
margins. Yeah.
yeah, and so it's one way that I read a paper just recently where they're talking about techniques of achieving adaptability. And they did a serious study of it. They looked at like 6 or 7 different techniques. The one that was the most effective in real world examples was design margin, having
Mm-hmm.
excess capability. That provides an incredible amount of flexibility and adaptability in real world situations. It's interesting that I thought that was an interesting outcome. Some people disagree with that, by the way. Some people in the
So is that
adaptability
part of
working
your
group.
resilience, techniques? Is that something that you guys consider? I mean, as best practice?
Yes, very definitely.
Okay.
But that's
Thank you.
also like looking at it from a risk management perspective. You got the cost of adding the margin,
Yes.
assuming how much margin you want to add. And then you've got the assumed cost of loss of capability. So now you've got to weigh, is it really cost effective to build
Yep.
in that extra margin or to
Yep.
do something else, or just to, depending on the nature of your system, if you have a loss of capability, just deal with it.
Yeah, it's kind of like buying insurance.
It is.
Yeah.
Hey,
You
John,
still
could you real quickly let people know from a resilience working group standpoint what products you have, guides, primers, or whatever, where they could learn more?
right now the majority of the material from the Resilience System Working Group is in the CBOC and in the Systems Engineering Handbook number 5. There's really good information in both of them. We are now in the process of generating both a primer and a guide for resilience. It's an ongoing process. We're in the middle of it right now. Okay, and just one last quick question, Francisco?
Yeah, thank you very much. A lot of work about taxonomy has been performed, and I'm very pleased to see that because, for instance, I just finished a meeting with the Corporate System Working Group. We have been discussing the relationship between terms like emergence, resilience, adaptability with respect to complexity. So there is a cross-cutting interest about taxonomy. You said that there are two communities. One is promoting the idea that resilience is just about recovering the capability after adversity. The other one is also embracing, avoiding, and withstanding the capability.
Yes.
I wonder if there is a slightly different solution that will embrace and consider both communities, which says that resilience is about the ability to recover the system capability after adversity by avoiding or withstanding or adapting or being agile. So the what is about recovering the capability, the how is all the terms like avoiding, withstanding, and so forth. I wonder if this slightly different view, but extremely similar, because I also agree with you that those terms are all very important, but could be a good solution to be more inclusive and consider all perspectives.
We really don't have time to go into it in depth. I can tell you that the working group has spent a lot of time thinking about this issue. We believe that avoid, withstand, and recover are mutually exclusive and exhaustive and cover most of the other terms that might be suggested. But let me leave it at that because, yeah, we would really need a couple hours to really delve into the point you're making. And I don't disagree with anything you're saying. The bottom line is you should be all inclusive. Anything that can achieve the resilience of that system should be considered by the engineer, in my humble opinion. Let me get into LDSE. LDSE, Loss Driven Systems Engineering, is a systems engineering area that addresses losses that could be created or mitigated by the system. LDSE unifies engineering domains that address losses associated with the system, and examples of that include resilience, safety, security, operational risk, CIPR, environmental protection, quality, and availability, and there are others, believe me. LDSE is intended to fill a gap in the systems engineering body of knowledge. LDSE applies coping strategies to manage loss of a value of interest, and that is something we refer to as an asset, due to an adversity. So you can see resilience is a type of loss-driven systems engineering. The asset of interest when it comes to resilience is the capability of the system. But now if you're talking about security, the asset of interest can be anything of value. You can secure anything from money in a safe to the trustworthiness of the data in your database to the capability of a system. That can also be secured. In a way, you can say resilience is the securing of the capability of the system. Oh, by the way, let me mention that I underscored those values. I'm talking about LDSE now because there was an LDSE project approved by INCOSE last March. We're about 6 or 7 months into it. We're starting to see some real good progress. But one thing we're finding is that whenever you talk about loss-driven systems engineering, you are talking about an asset of interest. You're talking about an adversity that could degrade the value of that asset of interest. You're talking about a loss metric that can measure that degradation. And you need to identify what is acceptable loss, to identify what the requirements should be for loss-driven systems engineering needs. And I am hoping we will be working with your working group to try to develop a pattern for requirements for loss-driven systems engineering purposes. We believe that systems engineering can harness the commonality and synergy of the loss-driven specialty areas to more effectively address system-related loss. This is the definition of systems engineering that was published by INCOSE. The fellows developed the INCOSE Systems Engineering and System Definitions document back in 2019. The bolding is my bolding. Systems engineering is a transdisciplinary and integrative approach to enable the successful realization of systems. I'll end it right there. The thing that we're addressing in the LDSE project is the fact that although the Systems Engineering Handbook and the CBOC do talk about loss-driven specialty areas like security, safety, resilience, adaptability, the handbook and the CBOC do not really address how those specialty areas should be integrated or the transdisciplinary principles that apply to all of them. That is what the LDSE project is going to try to achieve. Our objectives are to identify the transdisciplinary and integrative aspects of the specialty areas, develop working definitions of the loss-driven specialty areas, identify common and distinguishing characteristics of those disciplines, develop a harmonized vocabulary of common concepts so that those different areas can speak to each other effectively, develop a formal SysML modeling showing the relationship of the key concepts of those areas, develop common principles, tools, methodologies, and means of safeguarding assets and keeping losses acceptable that can be applied in all of the different areas. We believe we can develop patterns for loss scenarios, LDSE requirements, LDSE modeling, and shared risk management of all the different areas. We are planning to deliver a guide or a handbook for LDSE, hopefully by about this time next year. We hope to develop the transdisciplinary systems engineering level content for the next version of the handbook, and we will be updating the CBOC section on LDSE. Just to mention them, some of the areas where we find a lot of commonality between those different areas like safety, security, resilience, and so on, they're frequently thinking about the same assets of interest. They're frequently talking about the same types of loss, the same adversities, the same loss scenarios. They should be working with each other on that. They should be sharing information and addressing those problems together. Potential synergies among those groups include a shared vocabulary, shared modeling and analysis, shared requirements, shared architectural solutions, shared design solution, and shared risk management. We're hoping we can figure out how to make this happen and get it documented in the systems engineering body of knowledge. I won't go into any depth on this. One of the things we're working on is the key concepts and how they interact with one another. We are developing a formal representation of key LDSE concepts. This is an early draft. We're developing a typology of the different key considerations in the upper left-hand corner. These are the different types of asset that may need to be considered. Below that, in the bottom left, what are the different types of adversity that need to be considered? Upper right, what are the types of losses that need to be considered? And middle right, what are the coping techniques that may need to be considered? We're hoping to develop a typology that will help the system engineer consider all the possibilities that need to be considered. In terms of the transdisciplinary LDSE processes, we've developed a few draft recommendations. These are the things that would go into the technical process section of the Systems Engineering Handbook that are not currently, in general, most of these are not currently addressed in the handbook. First of all, identify the assets of interest potentially affected, and that is harmed or safeguarded by the system of interest. Identify the potential loss types, and that includes unintended consequences. Determine the level to which it is incumbent on the system to safeguard these assets. You need to know whether it's really the job of the system to worry about them or not. Establish asset loss limits. This would go into your requirements, of course. Identify the adversities, and these can be conditions, events, or things that could cause loss. Once again, this would have to be captured in the requirement. Identify system vulnerabilities that could lead to loss. Consider interoperating systems, and that is the systems external to the system of interest that may have a significant effect on the safeguarding of assets from loss or degradation. Number 8, nudge the stakeholders toward acceptance. Let me spend just a little bit of time on this one. I think this one's interesting, and I'm sure you've all run into this. The design of a system, the development of a system is usually focused on the needs that are top of mind to the stakeholder. In other words, why did they create that system? They are frequently not thinking about things like safety or security or resilience. These are things that are important, but it's not the fundamental reason for creating the system, and the stakeholders frequently don't think about them. And one of the jobs of the systems engineer is to act as a trusted advisor and make sure that the stakeholder understands the importance of security and safety and resilience and adaptability. The systems engineer has an obligation not just to educate them, but to help them make the decision about how much insurance am I going to pay for to achieve safety and security and resilience. And this is an interesting challenge that I don't think it's very well addressed right now in our body of knowledge. And I think we need to add some good thinking in this particular area. Number 9, generate loss-driven requirements. Then number 10, engineer the countermeasure that will achieve the needed safeguarding of the assets. And then manage risk and establish loss-driven change management and regression analysis. So anyhow, these are the processes that we've identified so far. This is really just an early draft, but I think we're starting to get some good traction. And I have one hand raised. Macaulay, do you have a question?
Yes, John, just a quick one. This is very interesting, the LDSE part, specialty engineering. So basically, from what you are saying, basically then we have a very big gap, the pain point in systems engineering as a whole, because if I'm designing a system that has to be deployed in nuclear reactor environment, and I know that I will have radiation effect in my devices, I should be able to talk to someone like you, a nuclear engineer, somebody that has good knowledge, so that I can have the proper requirements. So I'm glad that this is presented to the requirements working group. So that is what you would expect. So that means what you're telling us is that systems engineering is basically failing in being able to gather necessary requirements in things that we design, because we should be able to do that, because that's our specialty engineering, a part in this SAMP and everywhere, to be able to collect what is outside of my particular domain. And I go to these areas to be able to, to formulate my requirements appropriately. So is that what you're telling us, that basically this is a very big gap that we have in the systems engineering
It's addressed by the individual specialty areas. There's a lot of good thinking in the security community and a lot of good thinking in the safety and the resilience community. What is missing is the transdisciplinary thinking or principles and the integration of those specialty areas. And that's what we're trying to address. And we think there's a huge value that can be achieved by integrating those activities and identifying the transdisciplinary principles that apply to all of them.
Are you saying that this is a gap that we in the system joint community, or is it something that is lacking in the documentation that we produce in INCOSE?
Right now, I think it's a gap in the INCOSE documentation. Because, for example, the reason this all got started is I was working with a safety and a security engineer about 10 years ago on a particular project, and we realized that we could do a much better job if the three of us worked closely with one another. I'm sure that happens organically time and time again in the systems engineering and the engineering community, where people gravitate to one another and work with each other when they can be more effective that way. What we need to do is formalize it and get it into the documented body of knowledge, in my opinion.
In architecting systems and such, we focus on customer needs.
Yes.
One of those needs is to perform a mission. That's the reason why we have mission statements and goals and objectives that help us to see that. And
Yes.
You're absolutely right. These things that would prevent or hinder the accomplishment of that mission, because a lot of these fit into that category, are the things that we need to be looking at. And that should actually be traceable back to the satisfaction of those mission goals and objectives and why we need to consider these as we architect a solution.
Absolutely. I apologize in a way for not going back to the question of business needs and mission needs. When I say capability, I mean the capability of the system to support a business or mission need, of course.
I agree. That's what I'm getting at is part of what we should be doing as systems engineering is actually also uncovering the needs that our upstream stakeholders may not always recognize right off.
Yeah, that's what that nudge statement is about. It's part of our job to be the trusted advisor to the stakeholder.
To me, it fits naturally into what we talk about when we talk about our need and data-driven approach to how we establish requirements and architectures.
Yes. Okay, good.
When you talked about resilience, the focus was on adversity that could degrade or take away a capability.
Yes.
For loss-driven, it seems like you're going beyond not so much the capability, but we're actually losing something. We could be losing data or whatever. So,
yeah.
It seems like there's overlap here.
Very good point. When I talked about LDSE, it's all about a asset of interest, something of value. An asset is an item of value that you want to safeguard somehow. And security, for example, is kind of promiscuous. Security will secure anything of value, any asset of value. Resilience is more restricted. Resilience is interested in one type of asset, and that is the capability of the system. So resilience is really sort of a subset of security. Resilience is about securing the capability of the system. And so it's more focused, while security is more general. Does that make sense?
Yes.
Okay, yeah. Resilience is limited compared to security because it limits itself to interest in the capability of the system as the asset of interest.
Yeah, that makes sense.
John, I apologize, John. How does the robustness requirement fit into this discussion?
Robustness, as it's usually used, would be very similar to withstanding the adversity, the ability to withstand. Robustness does not usually consider either the avoidance or the recovery aspect of resilience. There's an overlap there. And by the way, there are a lot of other terms that overlap with resilience, and we do try to address that, but given today's amount of time available, I wasn't able to get into that.
Okay, thank you.
Here's an example of what we're capturing, methodologies and information sources. And I won't go through all of these, but let me just take a look at the first one, System Theoretic Accident Model. This was developed for the safety community. But you know what? I know right now people in the security area that are using it, and it can be used for resilience also. The same is true for all of these. We should be identifying all of the methodologies that apply to LDSE and making sure that all the different communities know about them and use them. The same is true for languages. I won't go through this slide in any detail. The working groups, okay, this is where it relates to the current INCOSE structure. We have 3 LDSE specialty areas under analytic enablers. That is resilience, safety, and security. Under the application domains, we've got anti-terror, CIPR, defense, and healthcare. And then under the process enablers, we have risk management and quality management. And I'm encouraging the requirements group is one of the groups I'd really like to get
Well, I was
involved.
going to ask about that because the requirements working group, you can go back to the NRM, you can look at other work that we're doing, looking at all of these things that result in LDSE. We wind up looking at how we're going to address them and capture those and not only define the appropriate needs, but the appropriate requirements, make sure that architecturally, as we're moving through the development of architectures, because to me, requirements and architectures are tightly coupled.
Yeah.
As we go through that, we need to understand these things. There's so much within what we do within INCOSE that we need to be integrating with
Yes.
the LDSE. I can talk to you human factors, our HSE working group. There's all these different things that as we start to look at, traditionally we haven't been as tightly coupled with as we should, but more and more I'm seeing there's a strong need for a tighter coupling.
Yeah, and just to foot stomp it, the list I show here are just the formal working groups. But for example, human factors is definitely a loss-driven concern. And so there are many specific loss-driven areas that I have not mentioned here that should be considered. I'm encouraging the INCOSE leadership to figure out how do we get these different groups to work together more frequently and more effectively. Just to point you toward a couple of pieces of information that are available on this. This loss-driven systems engineering initiative flyer is available. Also, there was an insight issue dedicated to loss-driven systems engineering that was published back in December of 2020. If you'd like to learn a lot more about LDSE, I encourage you to take a look at this. There's also a section in the CBOC on LDSE. LDSE project will be holding 1 or 2 working sessions at IW26. And at that working session, we're hoping to have representation from all of the working groups and communities that are interested in this particular area. And I really would like to identify a liaison requirements working group who can be an active member of the loss-driven systems engineering project.
If you need an RWG interface, this is Jeff Williams to use me, and then working with the other RWG leaders. If we need to have someone really focus on that, we'll work with the team and other members of RWG to see how to interact. As we're going through looking at joint projects and things of that nature that we would integrate, it may fit in with some of the things that we're doing right now in our current projects.
Okay, great. I will be in contact with you, and I warn you, I will be asking you to do some work.
That's okay.
I'd be glad to try to answer any questions you may have. Dave, you had a question?
Having been a program manager over time, I mean, and this is not a criticism, it's just more of a curious of a lot of the loss-driven system engineering to me looks like a risk management technique, right?
Yes.
For risk mitigation that I would identify in a program, technical risk, operation, that would be, and it would be a way to mitigate that risk. Hey, how am I mitigating? I'm writing a bunch of requirements to handle that, given if then type scenarios. Is that really what this is, or is it more than that?
Well, it's risk with a hardcore technical tinge to it. And in general, it's very operational oriented. It is applicable to the development life cycle also. Sometimes if I have to explain resilience to people, I sometimes will say it's really all about operational risk. How do you reduce the risk of the system not performing properly during operations? So yeah, risk is one side of the coin, and then safety, security, and resilience are the other side of the coin. We need to recognize that and bring them all together. You mentioned that you come from a program management perspective. When you mention risk, frequently people will think, well, risk is all about schedule, price, and capability of the delivered product. And this is a totally different type of risk. This is more about the risk during the operation of the system.
That's right. And as in the program wide, you're concerned, but you're definitely concerned about that kind of stuff as well.
Yes.
So,
And they're all legitimate. It's
yes.
just, risk is a very, very broad concept. It's very cross-cutting.
And it's neglected a lot of times. I'll say that.
Yeah, which, and well, that's where we need to train our project managers better. I'm much too much a coward not to have good risk management. Colleague, go ahead.
The last speaker, I think, points it out. So basically, I think all this is that we need to pay attention to our requirements, and like
Yes.
I say again, I'm glad that you brought this up to this working group, which has done such a great job, because what it means is that we don't really cover all our requirements well. And that's where we find problems at times in the deployment, because we always treat those specialty engineering as a stepchild requirements. Yes. Risk comes about, we just have risk readers and all this, but we don't have any type of requirement that we can point to. And until we begin to address that as a community, I think we will have this problem. So I think it's not managing our requirements or not developing requirements to address the specialty engineering aspect. There have to be requirements that we can point to and we can address, and we have to be able to satisfy them, to be able to test them. And I think that is a problem.
Let me amplify on that a little, because one of the things we've looked at is how do we need to modify or augment the technical processes that are in the current systems engineering handbook. And it turns out the ones that need to be augmented, which won't surprise anyone here, are the ones that occur before the requirements are pinned down. We need to identify the loss-driven issues during the business or mission analysis process, during the stakeholder needs and requirements definition process, during the system requirements definition process. And once you've gone that far, you can just throw the requirements in with the whole pile of other requirements and follow the normal systems engineering life cycle processes, and it'll pretty much take care of itself. But you have got to capture the assets of interest, the losses of interest, the adversities of interest early on before you write the requirements for loss-driven concerns. And once you've done that, you throw them into the hopper with all the other requirements, and things will kind of take care of themselves.
John, you're absolutely right. But what you just described is what I've seen over the last almost 50 years. That continual learning that we do from a systems engineering perspective, as we think we're beginning to grab all of the stuff that we need and beginning to understand how to architect our systems and develop the requirements. And we're learning new areas where we need to be focusing. And that's going to be nonstop. I got news for you. I guarantee you, a year from now, there's going to be people talking about other areas besides LDSE that we need to be focusing on. It's important. It's that continual learning that we have to do if we're going to be competent systems engineers.
Yeah, and just to repeat it, I know that people do this on their own in the background, and it's just that I think we do have a job in the INCOSE community to capture this, formalize it, document it, and promulgate it.
Oh, I agree 100%.
That's what we're trying. And by the way, I'm not criticizing INCOSE or the community at all. They do have bits and pieces of this, but I think we can get better.
I'm from the perspective that I think we always will be trying to get better.
Sure. Yes.
John, one more question. So requirements, working group engaged in this loss-driven thing that INCOSE is working on now? Because I think requirement working group be involved, collaboration.
I think as of this meeting you are. Jeff said that he wanted to start off as being the liaison to the...
Oh, God, yeah, well, Jeff is on it, yeah, because these are things that we always cry about in industry everywhere, that we don't do the systems work very well, meaning getting our requirements right, doing things right. So this is really, I think this is what they've been doing. This working group has been doing for many, many years. So I think they should be at the table to make sure that they have good guidance to go through this, because this is something that we should be doing. And if we're not doing it, then we just have to address those pain points. But it's not something new.
I think I can assure you we will do that.
Yes. I have a grand vision of us working not just with what they're doing in this particular working group, but with others. There's so much more we need to be bringing in and looking at how we integrate all of these disciplines to actually begin to give a better understanding. You know, just like we're working right now on the guide to model-based needs and requirements, which will hopefully be a great example on how to apply what you see in the NRM and an MBSE world. I'd like to see the same thing that is capturing all these other concerns that we have, how we go about addressing, how we go about identifying, how do we deal with the kinds of risks where we need to be looking at resilience and so forth. There's so much more we need to do if we're going to continue educating our systems engineering community.
Okay, and I see Karsten Wind. Karsten, what do you have?
Hello, Carsten Wind from Denmark. I have a question regarding to one of the first slides. You showed this graph about required capability, delivered capability, and I would like to understand it because I can, of course, understand that you can say the required capability, it degrades over time. And then I can see that the red one, so you imposes a stress and something that there's a reaction. My question is maybe two, because you say the delivered capability, first it rises again after the stress goes away, right? And I don't know if that a mitigation that happens or maybe a service engineer on site that do something. But why does, you can say, the delivered capability continues to rise?
I intentionally show it rising continuously because it's still below the nominal. It's not uncommon for there to be an immediate recovery that gets you just above the required capability so that you're meeting the needs, but then over time you may have a long-term recovery that brings you back up to the nominal state of the system. That's what I was trying to convey there. But once again, it's all about the recovery portion, and the system may be self-recovering, or the system might be part of a system of systems where it depends on external assistance to recover. And of course, we need to consider both of those possibilities.
Okay, so you assume that over time you will recover back to the normal, or will you always be below the, you can say, the first point?
It totally depends. This is simply a notional example. It could be that you won't go beyond just getting up to the required capability. It depends on the strategic long-term goals of the stakeholders and the owners of the system.
Okay, thank you.
Anand.
So my question is, like, what stage of project management or any product management we define the resilience matrix, and how it is different from the FMEA or safety related matrices?
Okay, well, FMEA would definitely be one of the methodologies that we believe people should consider in all of the different loss-driven specialty areas. With regard to the question you ask is, what technical processes during the life cycle does it come in?
Yep.
We have addressed that, and we've done an evaluation of the technical processes within the Systems Engineering Handbook, and we're drafting augmentations that are required for the purpose of loss-driven systems engineering. There are things that need to be considered that are not currently in there, and we're planning to augment that portion of the handbook in the next revision. But the interesting thing that we're finding is the place that it's critical to address loss-driven concerns is in the early period, during the needs analysis, during the business analysis, during the early identification of requirements. It turns out that once you get to capturing the loss-driven needs in high-quality requirements, after that, systems engineering will take care of them. Once you've got the requirements captured, you can throw them into the big pile of fundamental requirements, the ones that the stakeholder really cares about. If you have identified the loss-driven requirements, after that, the existing systems engineering processes will take care of them. They'll become part of the trade analysis. They'll become part of the architecture and design activities. The key is you've got to figure out what are the loss-driven needs and requirements early on in the life cycle.
In the Needs and Requirements Manual, Section 4 is the lifecycle concepts and needs definition part of it. And in there we have, during elicitation, where we're working with the stakeholders, and a lot of people focus on use cases or alternate use cases, but we specifically state in there to address misuse cases and loss scenarios. Part of
Great.
the upfront part. And then those are going to be identified. We're going to come up with concepts for dealing with those. And then the capabilities we need to deal with those will be communicated within the integrated set of needs, which will then be transformed into the design input requirements. So for your question, the guidance and activities covered already in the Needs and Requirements Manual.
Great. Yeah, you're
It is
anticipating
in
our
there.
needs.
And in what we're doing in the guide to model-based needs and requirements, we're already starting to look at how we look at some of those off-nominal things, not as thorough as I want it at the moment. When you begin to look first at your black box model, look at those interfaces, understand those interfaces, and look at them from the various threats along those lines, as you begin to do your FMEAs and look at your failure modes and how things fail, it drives you down all of that. And that's the reason why so much of this feeds in to the architectural aspects of how we actually determine what our requirements are, which comes back to working with our customers to actually understand the needs. We got to do all of that early on and understanding how we capture and document these requirements. And they're becoming increasingly important.
Yes.
And it's no longer, am I just looking at things from a reliability and a safety perspective? I'm looking at threats on those interfaces and things of that nature. That's growing much faster today than people realize. And it's so important that we look at those. And, misuse, there's so many ways to misuse systems.
Jeffrey, yeah, thanks for that explanation, right? So wanted to understand is how system right now is driven versus, as you mentioned, resilience is something which is very new and developing in systems engineering. What is the existing system and what is the delta that you observed or you think that will help if we implement resilience requirements in our system?
Within the resilience working group, we're hoping to deliver
Mm-hmm.
the two documents, the primer and the guide, that will augment what's in the systems engineering handbook to ensure that resilience can be properly addressed. Planning to do the same thing within the LDSE project to broaden it to include all of the loss-driven areas. And all I can say is I think we have identified the gaps that need to be filled, and we are in the process of getting those gaps filled. I think within a couple years we'll probably have the materials out there, and it may be incorporated in the next revision of the systems engineering handbook.
Thank you.
And by the way, the person we're working with in Fuse is, of course, Bill Miller, who many of you may know. He seems to be a strong advocate of the work we're doing.
Mm-hmm.
So I'm quite confident, given good consideration of where INCOSE is going. I think we've got leadership's backing on the work we've been talking about today.
I really like the topic. I think this is something that is needed. I don't think we put enough attention on loss-driven systems engineering. Of course, there's a number of areas I feel that way about, but this, I think, is very important. I see it as a natural collaboration on a lot of what we're doing as we begin to grow. And I agree that I actually think this is an area that is going to be an evolving area. Talking about pulling together in the next year or two, that's true about everything I wind up dealing with. I'm glad you brought this topic.
Okay.
There was a comment, John, from Christopher about the European Union has a regulation, the Cyber Resilience Act. They didn't know if you were aware of that or not.
No, I'm not. I know that within the U.S., the thing that really kicked resilience off was a presidential directive from Barack Obama in 2008. He declared that the U.S. space assets needed to become resilient. And the Air Force Space Command was working with MITRE, and they came to MITRE and they said, hey, what's this resilient stuff and how do we get some? That kind of kicked it off for us. And if you look at the account of the use of the word resilience within the systems engineering community, it was basically zero before that point in time, and it really took off in 2009, 2010. That's part of why I think there's so many different opinions about what resilience should be. It's a relatively new term. It's basically a stipulated definition, but then there's been a lot of work done on it, a lot, especially in the cyber community. So I'm not surprised that the Europeans may have a directive
Hello, this is Chris Rasplum. It's a regulation, it's a European law. So if you want to put something on the European market from 2027, you have to have cybersecurity requirements and you have to fulfill this regulation. And there are probably coming standards that you can fulfill in order to satisfy that law.
Okay, I'll keep an eye out for that too. I want to thank you for your time and attention. I hope you found it interesting. I have nothing else. I'll turn it back over to Kevin.
Very good. We thank you for a good presentation. It was well attended and excellent questions. Look like we got a lot more collaboration going forward, which is very good.
You bet.
So again, thank you for your time, John. Much appreciated, and we thank you.
Glad to do it, and I will be in touch.
Well, I think we'll call that a meeting.